Hello everyone. So it seems like we did a pretty good job with this fully connected feed-forward neural network with a few hidden layers. But we did have to do something a little bit bespoke that required a bit of audio knowledge, and that was taking the MFCC beforehand, so doing something with the MEL spectrogram. Now, some people who do neural networks would say, what we really want to be is not necessarily incorporating so much domain knowledge like this. It'd be nice if we could actually let the neural network learn for itself what's important. And this is a general theme throughout modern machine learning is we'll look at a task. Forever we were using something like MEL-spaced or even the Fourier transform. But it's like, hey, what if we just gave the network a little bit of flexibility? Maybe it'll learn something similar, but maybe it'll tweak it in just the right way to start doing a little better. So a lot of people want to create these end-to-end systems where we don't have these special steps in the middle. We just have more neural network layers or something. Okay, so I'm going to explain a way that we can actually drop in just a few more layers in the place of the MFCC and start with the raw audio and learn something that may or may not be like what the MFCC is doing, but learn something that will allow us to classify without having to use any of the stuff that we know, just neural network layers in the raw audio. So for this, I'm going to turn to a new kind of neural network layer called a convolutional neural network layer. And actually, this will be pretty familiar in a lot of ways because we've already done convolution before. Actually, this is a bit more like it's really correlation or cross-correlation. So it's a little bit more like what we were thinking about when we did autocorrelation, except we're doing it between two different signals. So here's how we can define this. So given an array of length k, or of length m, I should say, referred to as the kernel, k, we apply a convolution, or it's really called a cross-correlation mathematically, although for some reason AI people call it a convolution. We apply a convolution with an array x with n elements as the following. So we'll say, okay, the result of the convolution at element I, we'll say is yi. That is going to be the sum from, we'll say, j equals 0 up to n minus 1 of the kernel at index j times x at index I minus m over 2 plus j. Okay, now what the heck does all that mean? It's probably easiest to look at a few examples. So here's an example with a kernel that it's a rect. So this kernel is just a bunch of ones. And so what you do is you take that and you slide it along your input x, and you multiply. You're taking the dot product of that kernel in a little window with your signal, and then the output is the result of that dot product. All right. So the effect of this kernel on this noisy cosine here is to smooth out the noise, because we're taking a dot product with a whole bunch of samples. So ones with a whole bunch of samples. So this is just a running sum. So this has the effect of summing within the window. And so the noise kind of gets canceled out by summing over different terms. Okay, so let's look at some fancier examples. Here's one where the kernel is the derivative of a Gaussian. Okay. So what this looks like is as we're doing this sliding window, sliding the kernel past our signal, we're summing up some elements on the right side of where the window is centered on I, and we're subtracting the sum of some weighted sum of some elements on the left side. So what you can see is what I'm showing in orange is the pointwise product of this with the signal, and then we're summing up inside of here. And so this acts like a derivative, because derivative is always like something just in front of you minus something just behind you. And the limit, of course, but this is an approximation of it, more like a secant approximation of some sort. When I look at this, what I see actually makes sense, because I know that, okay, this is a cosine, and the derivative of cosine is a negative sine. And that's what I see, actually. I see something like looks like a sinusoid that actually goes down and then up and then down and then up. And so, and it also, this particular version has the advantage. So I said it's the derivative of the Gaussian. It's actually kind of like a smoothed derivative. So it has the advantage not only of taking the derivative, but of smoothing out noise. So you can see this is a pretty powerful idea, this convolution or cross-correlation idea of taking a kernel and sliding it across and getting the result of the dot products as you go. And so you can do a lot with it. So you can take derivatives. You can take second derivatives too. So here's an example of a different kind of kernel that would actually take the second derivative. So the second derivative of a cosine is actually negative cosine. And so you see this kind of interesting result here where it has the same shape except it got flipped upside down. So that seems like it worked. You can even go in and with something called a Gabor wavelet, which is kind of like a cosine, but it gets damped down at the end. And so if that had the right frequency, then it would actually line up perfectly with the signal, and we would get it back, possibly phase shifted. But if we went in with the wrong frequency, so this frequency is too high, then we wouldn't really get much out of it. So you can think of these in any number of ways. You can think of them like little operators that do something to signal. You can think about them like filters or probes, kind of like it was when we were doing the Fourier transform, except the difference here is we're actually doing it in a sliding window. We're not just probing the entire thing at once, we're actually probing as this slides along. All right, but so in terms of using these with neural networks, we're actually going to leave it open as to what the kernel is, and we're going to let the neural network learn what the kernel is. So first, let's just look at some code in Torch to do this, and I'll show you how we can at least represent and compute these convolutions, the cross correlations, and then I'll show you how we incorporate them into layers and then learn them. Okay, so you might notice the background changed. I'm back in my home office now. So let's see how we can do some of these convolutions with Torch. So what I did here was I copied some of the code that I used to generate the animations above. And what I'm going to do is create a layer in Torch that is what's called a convolutional layer. So I'll say, all right, layer equals nn.conv1d. It's helpful to look at the documentation. If you just throw in a question mark there, you can look at it. So there's three parameters that I'm really going to focus on here: in channels, out channels, and kernel size. So each different, you can actually roll a whole bunch of kernels into one, and each one of those is called a channel. And so my in channels is 1. So I've got one signal that I'm inputting. In fact, let me go ahead and put that over into Torch now. So I'll say actually x is equal to np dot or is equal to torch dot from numpy np dot array x d type equals np dot float 32. Make sure it's 32-bit float. And just to check, this is the signal I have. So this is that noisy cosine. And so what I'm going to do, though, is I have three kernels. I'm going to use a blurring kernel and then the first derivative and the second derivative. That's what I'm making with this code here. And so I will say out channels equals 3. And then I'll say kernel length or kernel size equals length of one of these. So I'll say kernel 1. Okay, so that makes this layer. And if I just go ahead and print out the parameters in this layer, what I will see, well, there's a lot, but so maybe I'll print an index 0.shape. So I see a tensor that is 3 by 1 by 200. So one input channel, 3 output channels, and each of the kernels is 200 dimensions. So what I can do is I can say, all right, say s is equal to layer dot get, let's see, I think it should be actually state dict. Yeah, okay, so there's this method called state dict. And then if I look at that, Okay, so what I can do is I can use this dictionary to change the weights. So I'm going to say, okay, S weights dot shape. Or S. Okay, there we go. Weight dot shape. So what I'm going to do is I'm going to set channel 0 to be the first kernel. Now you wouldn't normally do this, but I'm just, normally these are actually learned parameters. But for now, I'm going to just put in the ones that I have, just so I can show you how I invoke this layer. S weight 2 0 blah is equal to kernel 3. Okay, so this should be the 3 kernels I'm looking for here. So just to check it, if I now print layer dot parameters, I should now see. Oh, it says cannot assign. Okay, I gotta convert this to. Okay, I'll stop this for a second and get this ready. Okay, so I got all my parameters here, and so now what I can do is, well, let me just plot one of them just to make sure. So if I were to plot the layer dot parameters index 0, and I guess I'll plot maybe the first one. Oh, doesn't like that. Can't call a numpy. Okay, I have to say something. I have to say, there's so many little details here. I have to say dot detach. Okay, there we go. Anyway, there's the first kernel, and then just to check, here's the second one. Okay, so let me now try to apply this layer to my y, or I called it x here, to my x, to try to apply these 3 kernels to this signal. It's actually not going to work. I'll show you. It's going to throw an error. This one I know for sure is going to throw an error. If I try to say layer x, it's going to say runtime error, expected 2D unbatched or 3D batched input. That's because it's used to running these on batches of inputs, not just a single array here, but many at once in parallel, if it's on the GPU. So I've actually got to reshape my x here. So I'll say x, or actually I can say layer x dot view. And what I can specify here is that, okay, look, X currently has just one example, and then one channel, and whatever the length of X was. Okay, so this actually applies the layer to it. So I had to reshape. Okay, so I'll say here, reshape X so that it's 1 by 1 by 1,000. And so the dimensions here are, so this is a 3-dimensional array. So it's always example number by channel index. So we start with one channel, just this signal, and then by the number of samples. So this is a 3D array, and that's how it works. So we can, what we're going to do when we get the data loader, we're going to get a whole batch of these and apply them at once. So just let's have a look here at the output. So if I were to say y is equal to layer x, and I get this output, if I then go and plot y, well, it's not going to like that because it's a 3D array. I guess I'll say y 0 : : still doesn't like that. Okay, I need to detach it once again. Oops, and I should actually transpose it too. Okay, there we go. Anyway. So here's the signals that I get back. The first kernel was the blur kernel, so that took the cosine and just blurred it. Second kernel was first derivative, so I see first derivative. That's the orange there. It actually looks like, it turned out a little bit differently from what I expected. But I think that is because of it might have gotten reflected around here. Okay, but anyway. So that's how you apply a bunch of kernels. Okay, nice. but again, so this is stuff that I want to learn. So what I really want to do is replace the code that I have that used to do the MFCC here, and actually replace that with a network that has the first layer being convolution, with a bunch of different kernels that are then learned. So the MFC, the mail space spectrogram, occurred after doing a Fourier transform and then sending it through a filter bank. But we'll let the network learn whatever it wants, and so we'll leave it kind of open as to what the filter bank is at the beginning. So I'm just going to return the raw audio now. And I'll be careful to reshape it so that it's, starts off as a one channel thing. And then, all right, well, let's see if we can set up the model. So what I'll do is, actually I put this in its own cell because I'm going to want to mess around with it a little bit. But I'll say, okay, first I'll make a convolutional layer. So again, just conv1d, in channels equals 1, out channels. Well, okay, so how about this? When we were doing the Mel space spectrogram, we had 20 dimensions, right? But that was after we took the magnitude. So that, kind of actually needed 40 numbers first, the sine component, the cosine component. So maybe I'll go ahead and make actually 40 channels. Actually, another thing. Okay, so and then I have to determine the kernel size. So this audio is sampled at 8,000 hertz, and so the kernel size here is kind of like a window size. It'll be a sliding window. So maybe I'll define a window length fairly small, maybe 512, and then I'll define a hop length of half that. Actually, you know what? I'll make the hop length the same length as the window length for now. So there'll be non-overlapping windows. That'll make things a little bit easier. Okay, then I'll say kernel size is equal to the window. And actually, there's something else called stride, which is the hop. You don't have to slide these windows in increments of 1 each time. You can actually jump them ahead. And so that's a little bit more like what we did with the Fourier transform. We actually hopped along. Torch calls this stride rather than hop. So I'll just say stride is equal to hop here. And actually one parameter I forgot last time was bias. I'm going to keep that false for now. These can also come with an extra parameter for each channel, for each output channel, which is the bias. Okay, so how about this? All right, so I've got my first layer here. And somehow this is supposed to emulate, or this is supposed to be a drop-in replacement for the MFCC, for the flattened MFCC that we used before. So now, rather than specifying this up front, we're going to learn this. And so here's what I'll do. I'm going to create a data loader real quick just to kind of test this out and see the shapes. This is always very important. This is something I always do. So, okay, I got to load in this data first, but of course I need to also define the data loader first. Okay, now I load in the data. Whoops, I got a little bit ahead of myself there. I'll explain that in a moment. Okay, so load in the data. And what I'm going to do is take something out of the data loader that collates a bunch of together into a batch. So let me take that out and just see. So if I look at this x.shape, okay, so this is 64 examples, each with one channel, 32,000 samples of audio. That's right? 4 seconds of 8,000. Starts with a single channel. Okay, let's see what happens when we send that through the conv1. I'll say out is equal to conv1 of x. And let's just look at the shape. So x.shape was, I'll put that back there, and then let's look at out.shape. Okay, cool. So what happened here was, so we actually outputted 40 channels, right? Still 64 examples, but then 40 channels, and way fewer samples in each channel, and that's because we had this stride, right? So we're hopping along, and that's actually good because we don't want too many dimensions before we feed them into a fully connected layer, because we're about to go back and use basically what we did before and start to use the regular fully connected layers. So if I go back to what I was doing before, so let me kind of copy this in here so I have it. So eventually I'm going to want to go to these layers, And so dim, the dimension that I'm going to input into the first linear layer is going to be the number of channels times the samples per each channel. So I don't want that number to be too big because I don't want to have too many parameters. That's one of the reasons I wanted to hop by so much. So let's see, is that about, does that kind of make sense? If I had 32,000 samples over the hop length, 62, there it is, there's the magic number. So that's how many windows I end up having over each kernel. Okay, so I'm going to learn these kernels. All right, then I want to do something called flattening. I want to flatten this down. So right now it's expressed as a two-dimensional thing, but I want it to be one dimension. So I would like this to be kind of in the format that things were before, where I, when I did the MFCC, I actually flattened it. So it used to be a two-dimensional array, but I'm going to represent the same information by going row by row by row, laying them out into a one-dimensional array. So there's another layer that I need to make here. It's called flatten, that will do the flattening as part of the pipeline. So maybe I'll call this flatten equals nn dot, I think it's just flatten. let me check. I might have to tweak that a little bit. But okay, so if I do this and then, so I'll take the output and I'll say flat equals flatten the output, and let's just see if that worked. And it sure did. Okay, so 40 times 62 is 2480. So now I know that that's the dimension that needs to be input to the next layer. Now sometimes to avoid a magic number, what I'll do is I'll kind of send a test point through and I'll actually save the dimension in a variable. So I say I know, okay, the dimension that I need to go into the next layer, the input dimension is 2480. So I'll say, okay, that's just flat dot shape at index 1. So rather than having that number 2480, I'll actually just send an example through the first convolutional layer, and then I will flatten it and see what the shape actually is. Now I can go ahead and create these other layers. So let me put this all into a sequential thing now, because I think I'm pretty happy with how this is going. So what I'll say now is that my model equals nn.sequential. All right, and so the first layer is my conv1 is what I'm calling it. And actually I do want to do a ReLU after that. And then my next layer is going to be the flatten. And then finally I can just do exactly what I was doing before. So basically I'm just using this convolutional layer as a drop-in replacement for the MFCC. Otherwise, to keep this a fairly controlled experiment, I want to keep the other layers the same. So let's try that. So that's the model. Okay, so maybe I'll actually copy that code down here now. Invalid syntax. Then I missed a comma here somewhere, and then sequential. I missed the parentheses. Okay, there we go. Dim is not defined. I thought I defined it up here, but apparently I didn't. So, okay, so I'm going to let this train, and we'll see how it does. And I'll check back in.